everyone and welcome to Learning at 11th Hour. In this video, I'm going to show you how we can design a half subtractor and a full subtractor using combinational circuits. So let's begin. So when we talk about a half subtractor, it means that it's going to deal with just two inputs, one bit each. So say I have A and B as my inputs, I'll have difference and borrow as my outputs. So the inputs would be 0, 0, 0, 1, 1, 0, and 1, 1. So these are the combinations of the two inputs. So difference basically here is going to be A minus B. So 0 minus 0 is going to be 0. Therefore, there is no borrow involved. When I have 0 minus 1, it means that I can borrow 1. And so when I say 0 minus 1, if I'm able to borrow 1, then this number becomes 1, 0. 1 0 is in binary, which is nothing but 2 in the decimal number system. So 1 0 minus 1 is basically 2 minus 1. So the result of this is going to be 1. This is binary subtraction. So already we have 1 in the borrow, and after we include the borrow and try to subtract it, we get 1 in the difference. So this becomes 1 1. Next we have 1 minus 0, which is 1, no borrow. 1 minus 1 is 0 and no borrow. Now, looking at the difference column alone, along with the two inputs, we see that this is the expression for, this is the truth table for the XOR gate. So we can simply write that the difference is equal to A XOR of B. Even otherwise, if we look at the midterms, A dash B plus AB dash, which is the expression for XOR gate. Now, looking at the borrow, it is true only when A is 0 and B is 1, which means that the borrow here is going to be A dash B. So, when I represent it using logical gates, I'll have the two inputs A and B. And when I have the XOR gate put over here, what comes out is the difference. And A along with an NOT gate with B and it will give me my borrow. So this circuit over here is nothing but a half subtractor. Now let's move on to see how we can design a full subtractor using just the logic gates. So as far as a full subtractor or a full adder is concerned, we'll be having three inputs. Each of them would be 1 bit wide. So here again we have for the full subtractor, we have A, B, C as our inputs. The outputs would be the difference and the borrow. So the difference would be A minus B minus C. And in the process, if there is a borrow involved, then that particular input combination's borrow would be 1 or it would hold true. So 0 minus 0 minus 0 is going to be 0, borrow is 0. 0 minus 0 is 0. 0 minus 1 is difference 1, borrow 1, like I showed you. 0 minus 1 is difference 1, borrow 1, and 1 minus 0. So the difference here is still 1 and we are subtracting a 0 with it. So it will remain that and the borrow will remain 1. Next, 0 minus 1 is again 1, borrow 1. 1 minus 1, the difference will become 0, but the borrow will still remain 1. Next, we have 1 minus 0 is 1. 1 minus 0 is still going to be 1, but the borrow is going to be 0. So 1 minus 0 minus 1 is going to be 0, borrow 0. 1 minus 1 is 0, 0 minus 0 is 0, the borrow is 0. 1 minus 1 is 0, 0 minus 1 becomes 1, borrow 1. So this becomes the truth table of the full subtractor. Now we can design the full subtractor using the K-map. So for the difference, we can draw the K-map in this manner. So if I draw the grid, it's going to be a 3 variable K-map because there are 3 inputs involved. So I have A, and BC. This should be in the gray code representation. So 0, 1, 2, 3, 4, 5, 6, 7. I have numbered the midterms. So here if we see, I have 1, 2, 4 and 7. 1, 2, 4 and 7. So if you look at this K map, this is a brick wall kind of an arrangement. So we can directly conclude that this is just going to be A XOR of B XOR of C. So you can refer to my previous video on full adder, where I would have derived the expression entirely. So this is the expression for difference. Next, we can derive the expression for borrow. So for borrow, again, I have to draw a 3 variable K map. So here we have A, B, C, 0, 1, and this is going to be numbered as 0, 1, 2, 3, 4, 5, 6 and 7. So if you notice, the midterms are 1, 2, 3 and 7. So let's try and fill the midterms over here. So we can fill it up as 1, 2, 3 and 7. Now let me try and group it. So here we are only going to get pairs of adjacent ones. So this is the first one, first group, and the expression for this. So if you analyze the row, A dash is common to both the midterms, and if you analyze the columns, C is common to both the midterms because it is 1, 1 for both the midterms. So I'll put C over here. The second group is going to be this pair, and the expression for this is again A dash from the row, and if you look at the column, it's going to be B. Now the third group, I can group these two midterms together, and then it becomes BC because A is not going to be common for both the midterms. Only B and C are common and both of them are 1. So put together, the expression for borrow actually becomes A dash C plus A dash B plus BC. So now I can implement this using logic gates. So what I would get here is, um, I have A, B and C. A and B XORed along with C XORed again. This is going to be my difference, which is A XOR B XOR C. Now the borrow is going to be A dashed C, A dashed B. So what I really need here is an inverted A. So I'm going to draw A dash over here. So this is A dash. So A dash along with B. Again, I can have A dash along with C. Both of them are ORed together. So here what I have is A dash B plus A dash C. Now this is ORed with BC. So I need BC. So I have B here, I have C here, another AND gate. This would provide B dot C. And this is again ORed with the rest of the terms. So here I get the expression for borrow. So this is the design of a full subtractor. Now this is not a full subtractor using two half subtractors yet. So this is just with the help of logic gates. If you want to implement this using two half subtractors, you just need to modify the expression for borrow a little bit, and then you can get it. So let's see how we can design a full subtractor using two half subtractors. We know the expression for our difference is going to be A XOR B XOR C, and the expression for borrow was A dash B plus A dash C plus BC. Now we're not going to modify anything with the difference, only the borrow part we're going to modify. So what we're going to do is, so we have A dash B over here. Let's keep it as it is. Let's try to modify this. I'll tell you why we are doing this, right? So to begin with, suppose I have a half subtractor, HS1. Think of it like a black box. And I am going to provide two inputs to it. So this is going to be A, this is going to be B. So what will come out as difference would be A XOR of B, and what will be coming out as borrow is going to be A dash of B. Now we are going to have another half subtractor over here, and one of the inputs to it is surely going to be C, and the other one is surely going to be A XOR B. That's because we know that whatever we send into this black box, the difference is going to be the XOR of its inputs. So if one of the inputs is A XOR B, it will be XORed with the second input. So that's C in this case. Now, what is going to be my borrow? So that will be, if I consider this as say X, it's going to be X dash C. That means it's going to be A XOR B whole bar into C. Now, uh, there is this term A dash B, which is also there. So we have to combine the borrow coming out from HS2 and the borrow coming out from HS1 in such a way that we get this particular expression. So if we observe, we already have A dash B here coming, so we'll keep it intact. We have to manipulate the rest of the expression so that we get something similar to this. So what we can do here right now is we can uh, convert this into a canonical form. So whatever is missing, we're going to include it. So I'll write this as A dash C, B plus B bar, and I'll write this as A plus A dash into BC. So when I expand this, I will get A dash BC, A dash B dash C, A B C, A dash BC. Now, if I take C common from these two expressions, so I have C over here, A dash B dash plus AB. This is what comes out. And if I look at these two terms, both of them are one and the same. So they are redundant. So I'll just neglect one and retain only one. So A dash BC, and this will come down as it is A dash B. Now, looking at these two expressions or these two terms closely, if I take A dash B common, I'll get 1 plus C. And here I'll retain whatever is coming. Next, 1 plus C is going to be just 1. So I have A dash B, which was coming out from the first half subtractor, and C into A XNOR of B, which is A XOR B the whole bar. Because if you look at this expression, it is A bar B bar plus AB, which is nothing but A XNOR of B. So that is the complemented version of XOR. So now this becomes very simple because this term is already available to us at the output of my second half subtractor, and this term is available to us at the output or the borrow of the first half subtractor. So all I need to do is include an OR gate to combine both the borrows. So to do that, let me just include one OR gate over here, and then call this as my borrow, and this is going to be the difference of my full subtractor. So this is how we can implement a full subtractor using two half subtractors. So I hope this concept of full subtractor, half subtractor, and implementation of a full subtractor using two half subtractors is clear to you all. If you have any queries, please do not hesitate to post it in the comments. Thanks a lot for watching.